This is obviously credited for this guy who kind of looks like a rock star, I think. Dale Hospital, not hospital, okay? Hospital came up with this rule. He was actually started teaching college when he was 18 years old. So he was a pretty bright guy. And back in his day, calculus was kind of new. So there was a lot of mathematicians working on the idea of calculus. So his thing is, and we've seen how to do limits, and you can have limits of a 0 over 0 form. We saw that over and over again when we did limits. And we also looked at, we didn't really talk much about it, but we saw some that were infinity over infinity forms like this. So what I want to show you first of all is in these two examples, like if you just plugged in to the sine x, you would end up doing sine 0 over 0. And that should say sine of 0 radians over 0 radians. The sine of 0 is 0. That's what we call a 0 over 0 form. Now, it doesn't mean that we're doing 0 divided by 0. That's just a form of that. So L'Hopital's rule is going to say that we can differentiate. We can do the derivative of the numerator and denominator, then attempt to reevaluate the limit. Okay, this one right here, if you plugged in, you don't really plug in infinity, but it helps you to think through this problem. If you're doing this, so wouldn't the numerator be an infinitely big number? 2 times infinity is infinitely big. Minus 3 is still infinity. So that would be what we call an infinity over infinity form. So typically we did some sort of an algebraic process to work out the limit. Most of the time it was factoring, rationalizing denominators, stuff like that when we learned how to do this. So L'Hopital's rule basically says these things. So it says your two functions have to be differentiable. You're looking at the form a limit of f over g. You have a rational type of function. Okay. So basically it says as long as they're differentiable, those two functions are differentiable, and then the derivative of g can't be 0 because then you would have a 0 denominator. Okay. Then the idea would be that if you want to work out this limit, if it's already in a 0 over 0 form or infinity over infinity form, then you can do the derivative of top and bottom, then you can reevaluate the limit. Okay, that's what L'Hopital's rule is saying. Okay, so what I'm going to do is on the next page, I'm going to go ahead and do some limits using L'Hopital's rule. We're going to do some of the simpler ones today. So first of all, again, if you look at this example right here, if you're doing the limit x goes to 0 of sine x over x, first of all, don't just go immediately into doing L'Hopital's rule. Make sure it's a 0 over 0 form or infinity over infinity. So if you plug this in, we'd have sine 0 over 0, which is the 0 over 0 form. Okay, make sure it's that. Now, when you do L'Hopital's rule, here's basically what you do. Okay, you say the limit as x goes to 0 of sine x over x equals, okay, and I like to, this is, I guess, my notation. I like to put a little h there because it's by L'Hopital's rule. We do the derivative of the top and bottom. Okay, so what is the derivative of the sine? Cosine. So this is going to be the same as evaluating the limit cosine x, and then what's the derivative of the bottom? 1. Now we're going to retry the limit, and we're going to see what we get. Okay, so if we do that, let's just plug the 0 in. So now we're going to have cosine of 0 over 1. Now on a unit circle, the cosine of 0 is the 0.10, so what's the cosine? It's the x value, right? Okay, so what you'd end up having is 1 over 1, or the answer to that limit's 1. That was a limit that we developed using a calculator. I kind of showed you how to develop that idea, but L'Hopital's rule would prove that the limit of sine x over x is equal to 1. So it gives us a powerful tool to do more limits of different sorts. Okay, does that make sense what I did? Now, as long as the derivatives are easy, students usually don't have much trouble with L'Hopital's rule. They can get a little messy like anything else we do in calculus. So this next one, the first thing I want to do on this is look at again, what kind of form do we have? So you're looking at a limit as x goes to infinity. So you're really doing 2 times infinity over 3 infinity plus 1. Okay, the numerator is infinity, isn't it? So is the denominator. So since it's that form, L'Hopital's rule applies. But you got to make sure that it's either this form or this form before you go running in and starting to do L'Hopital's rule. Okay, so what we're going to do is this one works out real easily. So we're going to do the limit as x goes to infinity of 2x minus 3 over 3x plus 1. And we're going to do L'Hopital's rule. Okay, so this one's easy. What's the derivative of the top? What's the derivative of the bottom? 3. So we got a limit of a constant now. So we have the limit as x goes to infinity of 2 over 3, which is 2 over 3. Okay, now there's another thing you guys learned on this, and you actually learned this like in college algebra. Okay, that's a rational function. What's the degree of the top? 1. What's the degree of the bottom? So you learned in college algebra that this is a horizontal asymptote at y equals 2/3. L'Hopital's rule kind of proves that that will always work in that case. All right, so it does simplify the way we do lots of limits, doesn't it? Okay, so does that make sense? Okay. So again, be sure that when you're doing these problems, I'm going to do these next down here, and I just took these out of the book, that you verify the form first of all before you do anything else. So let's plug in on this one, just plug in 0. So we have e to the 0 minus 1 over 0 to the second plus 3 times 0. So what's e to the 0? Okay, so it looks like we got 0 over 0, right? Verify it. You can a lot of times do that in your head too. Okay, so we know that L'Hopital's rule can be used on this one. And if you didn't know L'Hopital's rule, you wouldn't really be able to do much with this other than use some technology to try to figure this out. Okay, which is what we did earlier in the semester. So what we're going to do is, since we now know that you can use L'Hopital's rule on this, well, what do? What does L'Hopital's rule tell you to do? Do the derivative of top and bottom, and then try again, basically. All right, do whatever you can do in your head. This one shouldn't be too bad. What's the derivative of e to the x minus 1? E to the x, okay. What's the derivative of the bottom? 2x plus 3. Okay, so what we're going to do is just going to try again, see what happens. So we're going to plug in the 0 now, so everywhere you see an x, plug in a 0 now and see if you get an answer. So what we're going to have is e to the 0 over 2 times 0 plus 3. So that's 1 over 0 plus 3. So it's 1/3. So that's the answer. That's the limit. Now you could tell that you're right on this problem by graphing it on a calculator, and I want to encourage you to do those kind of problems, particularly if you ever get stuck on doing a limit. Look at that on your calculator, and you could check this, because you could plug in a number barely to the right and barely to the left of 0, and it would approach 1/3 based on the stuff we've learned earlier in the semester. Okay, does that look okay? Okay. So L'Hopital's rule sometimes is pretty simple. Okay, let's try this next one here. Okay, go ahead. Always evaluate your limit first to make sure that L'Hopital's rule applies. Don't overlook that. So we have e to the 0 minus sine 0 minus 1 over 0 to the 4th plus 8 times 0 to the 3rd plus 12 times 0 to the 2nd. Now, if you can do all this in your head, that's fine with me. What do we have? E to the 0 is 1. The sine of 0 is 0. And you can pretty well tell that the denominator is 0. So that's definitely a 0 over 0 form limit. Right? Make sure, though. Do all the details of the arithmetic. Okay, so far so good? Okay, so it's 0 over 0 form. So what we're going to do is we now know that we can apply L'Hopital's rule. So we're going to do a derivative, reevaluate, and see where that takes us. Okay, this again will be a fairly simple derivative to do. Generally, I have students write equals with h. You don't have to do that. That just means that you're applying L'Hopital's rule. Okay, so in your head, can you do the derivative of the numerator? E to the x minus cosine of x, right? Okay, so we're going to have e to the x minus cosine x. Now the denominator is going to be 4x to the third plus 24x squared plus 24x. Okay, like that. Now we got to plug in and see what happens. Now I can do this in your head, you can too. What's going to happen if you plug 0 into the denominator right now? And have 0. And if you plug in 0 to the numerator, you're going to have e to the 0 minus cosine of 0, which is going to be 1 minus 1, or 0. So again, it's a 0 over 0 form again. But L'Hopital's rule says you can just do it again. And you can do it again and again and again, okay, until something happens. So that's what we're going to do, is we're going to apply L'Hopital's rule again. Okay, sometimes you have to do it a couple of times, sometimes 3 times. Not too much more than that, though. Okay, so yeah, you got to just do L'Hopital's rule again. So don't give up on it. It's still 0 over 0, so that means L'Hopital's rule is going to work again. Okay, so we're going to have, what's going to be the derivative of e to the x minus cosine x? Okay, good, plus. Now remember, you have minus negative sine x. Okay, now the denominator is going to be 12x to the second plus 48x plus 24. So that's going to give us the limit as x goes to 0 of e to the x plus sine x over 12x squared plus 48x plus 24. Okay, now look at the denominator. The denominator is going to be what in your head? 24. Okay, so that's good. The numerator is going to be e to the 0 plus sine of 0, so it's not going to, so I think we're good. So what we're going to go ahead and do is work out the arithmetic. So we have e to the 0 plus sine of 0 over 12 times 0 squared plus 48 times 0 plus 24. Okay? So what's the numerator going to be? 1 plus 0. The denominator is going to be 24. So, believe it or not, the value of that limit is 1 over 24. If you graph that on your calculator, if you went just barely to the right of 0 and the left of 0, it would be approaching 1 over 24. Yes?
So for tested over limits on the final, can we do this? Or will you specify?
Oh, that's fine. That's fine. If I gave you a limit and it was, if you could do it by L'Hopital's rule, please do it. Okay? Because a lot of times it's easier.
Yeah.
You know, sometimes any of the limits that we did earlier in the semester that are either 0 over 0 or infinity over infinity can be done this way now. Okay?
So whenever you have infinity, can you just sub in 0 for it? Or
say that one more time?
Because whenever the limit is x to infinity, can you just sub in 0 for it?
Well, you really just kind of think about x being infinity and seeing what happens. So if you kind of look at this problem up here, right here, I'm really just thinking of x as being infinite. And if you do 2 times infinity minus 3, that's an infinitely big number. That's all we care about. Okay, we're not doing arithmetic. We're just saying that's going to be infinite, that's going to be infinite. Okay, so if you plug infinity in, you're looking to see that the numerator is infinite and the denominator is infinite. If it is, then L'Hopital's rule applies. That's the idea. Okay, so let's finish up with this last one here, and then I'm going to focus on the more difficult ones in the next class. So first of all, let's go ahead and plug in. So we have tangent of 4 times 0 over tangent of 7 times 0. Okay, so this is going to be the tangent of 0 over the tangent of 0. Okay, like that. Now, what's going on this? If you look at a unit circle, you have 1 over 0. Remember, the definition of a tangent is y over x, right? So what is the tangent of 0 going to be? It's going to be 0 over 1, so it's 0, right? Okay, can't forget the tangents y over x. So we do have a 0 over 0 form limit like that. Now there's a tendency a lot of times to want to just cross that out and make it 1. It's not really the case. This is an indeterminate form of a limit here. So that expression is going to be evaluated as 0 over 0. So this is going to be something you could use L'Hopital's rule for because it has the right form. Okay, so we're going to go ahead and do L'Hopital's rule, and we're going to see what happens. So you got some trig going on here, so you got to pay attention to those are z's, I think, aren't they? Yeah, okay. Doesn't really matter, but let's be consistent here. Okay, so we got 4z over 7z. Z goes to 0. Okay, so by L'Hopital's rule, what is the derivative of the tangent? You need to know that for your gateway test, and if you don't remember it, you at least got to know how to derive it. So it's secant squared. So this is going to be secant squared of 4z, but then what else you got to do? Got to do the chain rule. So you got to multiply by 4, right? Okay. The derivative of the bottom is going to be the same way. It's going to be secant squared 7z times the derivative of 7z, so it's going to give that. Now what you have on this is you have a constant. And you don't necessarily have to do this, but I want to remind that you can. A constant can always be taken out of a limit. So you could write this as 4/7 times the limit as z goes to 0 of the secant squared of 4z over the secant squared of 7z. Okay, so we're going to look back at 0 again and think about this then. Now the secant is, what's the definition of a secant in a unit circle? It's just the reciprocal of the cosine, right? So it's r over x. So basically all the secant is it's the reciprocal of 1, right? So what's the reciprocal of 1? It's 1. So what you would end up having then is when you evaluate this limit, you would have 4/7. And you can write this as secant of 4 times 0 to the second. And you can do this in your head. I mean, you don't necessarily have to write this step this way, but you are evaluating that limit like that. So what you end up getting is 4/7 times 1 to the second over 1 to the second. So that means the answer to this problem is 4 over 7. Okay? Now that secant, remember, is the reciprocal of the x value on a unit circle. So when you're plugging in and doing the secant of 0, you get 1. Yes?
So are they technically the same degree? Kind of like when you're looking at a polynomial that's the same degree?
That degree is really talking about polynomial functions. And you're seeing this kind of the way you see horizontal asymptotes on a polynomial. Now on a tangent like this, I mean, you could probably prove that the tangent of AZ over the tangent of BZ is A over B. You could prove that with L'Hopital's rule, so it works. Okay, and it's just something that works on the tangent. I think it works on a cotangent also. Okay, all right, well, that'll finish this up for today.